Our journey today will take us to the bleeding edge of astrophysics, to the places where our knowledge ends and the grandest enigmas begin. We'll explore phenomena so bizarre, so counterintuitive, that they challenge the very foundations of what we think we know about reality. These aren't just science fiction concepts. They are real, observed puzzles that keep astronomers and physicists awake at night. We're about to embark on a journey through 7 of the most mind-bending mysteries the universe has to offer. From the absolute coldest spot in existence to invisible structures that hold galaxies together, we will confront the unknown. Prepare to have your perspective shifted, your curiosity ignited, and to be reminded that the most beautiful thing we can experience is the mysterious. It is the source of all true art and science. Let's begin. Let's begin our journey with a destination that defies our earthly intuition about temperature. We often think of space as cold, but what if I told you there's a place so frigid it makes the vacuum of space seem balmy? Travel 5,000 light-years away to the constellation Centaurus. There we find the Boomerang Nebula, not a place of fire and fury, but of almost absolute cold. At a staggering 1 degree Kelvin, that's minus 458 Fahrenheit, it is the coldest known natural place in the universe. Even the cosmic microwave background is warmer. How does it get so cold? The answer: a dying star at its heart. A star much like our sun. In its final, dramatic throes, it's shedding its outer layers, ejecting gas at over 370,000 miles per hour. This rapid expansion is the key. Think of it like a cosmic refrigerator. Like when you spray an aerosol can, the can gets cold as gas expands. The Boomerang Nebula does the same on a galactic scale, a process called adiabatic expansion. Gas molecules use their own thermal energy to push outward, cooling themselves to record low temperatures. This celestial ghost, shaped like a bow tie, or, as the name suggests, a boomerang, is a pre-planetary nebula. A fleeting stage lasting only a few thousand years before it becomes a planetary nebula. We are fortunate to witness this chilly moment in cosmic time. The light we see left 5,000 years ago, a snapshot of its past, a frozen echo of a star's last gasp. Even in death, stars make objects of chilling beauty, pushing physical limits. This object challenges our models. The rate of gas expulsion and the resulting temperature are more extreme than predicted. It forces us to refine understanding of how stars die, how they interact with the interstellar medium, and the thermodynamics of the cosmos. The Boomerang Nebula is a crucible for our theories. It whispers, "There's always more to learn. Something colder, something faster, something stranger than we ever imagined." Imagine you're a radio astronomer listening to the silent symphony of the cosmos. Your giant telescope dish is tuned to the faint hum of distant galaxies and pulsars. But just as you register its presence, it's gone. The entire event lasted for only a few milliseconds, a thousandth of a second. You've just detected a fast radio burst, or FRB. These are one of the most perplexing mysteries in modern astronomy. Cosmic chirps from an unknown source, arriving without warning and vanishing without a trace, from galaxies billions of light-years away. The sheer distance they travel tells us that the source must be cataclysmically powerful. Think about it. For a signal to traverse billions of light-years and still be detectable by our instruments on Earth, its origin must involve an almost unimaginable release of energy. What in the universe could produce such a brief yet monumentally powerful flash? The list of suspects is long and exotic, and frankly, we just don't know the answer. We found that some FRBs are one-off events, like the collision of 2 neutron stars or the final collapse of a massive star into a black hole. But then, to complicate things, we found repeaters. One famous repeater, FRB 121102, has been observed to burst hundreds of times. This completely rules out a self-destructing source. A repeater needs an engine, something that can recharge and fire again and again and again. So what could it be? The theories are as wild as the phenomenon itself. Perhaps they are flares from magnetars, a type of neutron star with an insanely powerful magnetic field, 1 billion times stronger than anything we can create on Earth. A starquake on the surface of such an object could certainly release a tremendous amount of energy. Other, more speculative ideas range from cosmic strings vibrating through space to, yes, even signals from an advanced extraterrestrial intelligence. While we have no evidence for the latter, when faced with a mystery this profound, scientists must keep an open mind. Each new FRB detected is a clue, a piece of a puzzle that could rewrite our understanding of extreme physics. Our galaxy, the Milky Way, is not stationary. It's hurtling through space at a staggering 1.4 million miles per hour. But what's pulling us? For decades, we knew we were moving towards the Virgo cluster of galaxies. Even after accounting for Virgo's pull, there was a residual motion. A mysterious velocity vector pointed toward a different region of space. Something else, enormous and unseen, was tugging on us, and on thousands of other galaxies in our cosmic supercluster. We call this enigma the Great Attractor, located about 150 to 250 million light-years from us. The Great Attractor lies in the zone of avoidance behind our galaxy's disk of stars, gas, and dust, like trying to see a mountain range through a blizzard. Thanks to advancements in X-ray and radio astronomy that can pierce the galactic dust, the picture became clearer and more complex. The Great Attractor isn't a single colossal object. It appears to be the gravitational focal point of a massive supercluster of galaxies, known as the Laniakea supercluster. Laniakea, meaning immeasurable heaven, contains the Milky Way. It's a sprawling filamentary network, a valley toward which everything is flowing. Mapping Laniakea showed the entire supercluster, including the Great Attractor, is being pulled towards something even more massive, the Shapley supercluster. The Great Attractor is a cosmic way station on a much grander journey. We are part of a great cosmic river, a flow of galaxies stretching across hundreds of millions of light-years, all drawn by the inexorable, invisible hand of gravity. We are all familiar with the concept of a black hole, a region of space-time where gravity is so strong that nothing, not even light, can escape. It's the ultimate cosmic prison. But what if there were an opposite? A cosmic object that nothing can enter, a place from which matter can only flow outward, a place from which energy can only flow outward. This is the theoretical concept of a white hole. It is the time-reversed solution to the same equations of general relativity that predict black holes. Where a black hole is an eternal trap, a white hole would be an eternal violent fountain. Imagine a white hole. You couldn't visit it. As you approached, you'd face an ever-increasing torrent spewing out at the speed of light. Any object you threw would never reach the event horizon. It would be like trying to drive up a waterfall flowing faster than your car. Mathematically, they are valid possibilities. But in the real universe, we've never seen one. They remain hypothetical, a ghost in the mathematical machine. Black holes form from collapsing massive stars, but there's no known process to form a white hole. So why do physicists talk about them? Because they offer speculative solutions to big physics puzzles. One idea: white holes connected to black holes via wormholes. Imagine an Einstein-Rosen bridge diagram. Matter falls into a black hole in one part of the universe, or perhaps in another universe entirely, and could be violently ejected from a white hole elsewhere. That suggests inter-universal travel, or the transfer of information across cosmic distances, potentially addressing the black hole information paradox. Another idea: the Big Bang might itself have been a white hole, a singular event from which all the matter in our universe erupted forth, and all the energy. An event with no prior state in our space-time. The math for a supermassive white hole resembles the math for the birth of our cosmos. Could our universe be the result of a white hole explosion 13.8 billion years ago? It's a mind-bending connection between our beginning and this exotic object. For now, white holes remain a beautiful and elegant mathematical, what if, Chapter 6. Let's shrink down from the cosmic to the quantum, to the realm of the very small. This is the world of quantum entanglement. Albert Einstein famously called it spooky action at a distance. Imagine you have two particles, say two electrons that are created together. They are now entangled. Their properties, like spin, are linked. If one particle is measured to have a spin up, you will instantly know its entangled twin will have a spin down no matter how far away it is. The outcome of one measurement instantaneously influences the other. This connection is instantaneous, seemingly faster than light, which conflicts with Einstein's relativity. It's not that information traveled that distance. The particles aren't separate entities the way we think. They're part of a single quantum system described by one wave function, regardless of physical distance. This isn't just theory. It's been experimentally verified, even using light from distant quasars billions of light years away, to ensure measurements were truly random. The universe really is this spooky. This shatters classical intuition about cause and effect and challenges the nature of space and locality. It suggests a deep, non-local reality underpinning what we see. Some physicists speculate entanglement links to the fabric of space-time. The ER=EPR conjecture proposes that two entangled particles might be connected by a microscopic wormhole. The spooky action may not be action at a distance, but a shortcut in space-time geometry. Could entanglement be the thread of space-time? This idea tries to unite quantum mechanics and general relativity, suggesting the quantum world's strangest feature could be the source of gravity in space. Chapter 7. Our universe is vast, perhaps infinitely so. The part we can see, the observable universe, is a sphere about 93 billion light-years in diameter. This boundary exists because light from beyond that distance hasn't had enough time in the 13.8 billion years since the Big Bang to reach us. But what lies beyond that horizon? Is it just more of the same? More stars, more galaxies, stretching on forever? Or could it be something else entirely? The multiverse isn't one idea, but many, from different areas of physics. One popular version comes from cosmic inflation. In the first fraction of a second after the Big Bang, the universe underwent exponential expansion, growing from smaller than an atom to larger than a galaxy almost instantaneously. The math suggests inflation, once started, might never completely stop. It might stop in our region, allowing our universe to form, but continue elsewhere, spawning an endless cascade of bubble universes. In eternal inflation, our universe is one bubble in a frothing cosmic foam. Each bubble could begin with slightly different conditions. That could mean the fundamental constants of nature, the strength of gravity, the charge of an electron, the speed of light, might differ in each universe. Most of those universes would be sterile, unable to form stars, galaxies, or life. A slightly stronger nuclear force. All hydrogen fuses into helium at the Big Bang. A slightly weaker force. Stars can't ignite. This offers a possible explanation for the fine-tuning problem, that the laws of our universe are exquisitely balanced to allow complex structures like galaxies and life. If countless universes exist with random laws, it's not surprising we find ourselves in one where conditions are just right. We exist because we can exist here. This is the anthropic principle. While we currently have no way to test this or communicate with other universes, the multiverse remains a compelling and, for some, necessary consequence of our best cosmological theories. When we look at the universe on the largest scales, we see that galaxies are not distributed randomly. They are arranged in a magnificent, intricate pattern, a vast network. Clusters, superclusters, connected by long, tenuous bridges of galaxies. This structure is known as the cosmic web. But what holds this web together? What is the invisible scaffolding upon which the luminous matter we see is built? The answer is dark matter, specifically, dark matter filaments. These are colossal, invisible threads of dark matter that stretch for hundreds of millions of light years across the voids of space. Dark matter is a mysterious substance that does not emit light. It does not reflect light. It does not absorb light, making it completely invisible to our telescopes. We know it exists because of its gravitational effects on the things we can see. It's the unseen mass that keeps galaxies from flying apart. It also bends light from distant objects. Our cosmological models predict a massive web-like structure. The galaxies we see are just the Christmas lights decorating this invisible cosmic tree. They congregate in the densest parts, the nodes and the filaments. Imagine running a simulation of the early universe. Gravity pulls over densities together. Dark matter dominates. Filaments form first. Gas flows in. Galaxies arise like water into a riverbed. The cosmic web we observe today is a direct visual confirmation of this underlying dark matter structure. Recently, astronomers have made the first direct observations of these filaments by studying the faint light from distant quasars, subtly absorbed and distorted by gas trapped within the dark matter filaments between the quasar and us. It's like seeing the shadow of the web. This confirms the filaments are real, and that our model is correct. We are mapping the invisible skeleton of the cosmos, a skeleton that dictates where galaxies are born, where they live, and how they evolve. It's a profound realization that the grandest structures we can see are shaped by a substance we cannot. Outrow, we've journeyed from the coldest place in creation to the theoretical edge of reality itself. We've encountered rogue planets wandering in eternal night, listened for whispers from cataclysmic events billions of light years away, and contemplated the invisible structures that shape our universe. The Boomerang Nebula, fast radio bursts, the Great Attractor, white holes, quantum entanglement, the multiverse, dark matter filaments, serves as a powerful reminder. It reminds us that we live in a cosmos that is not only stranger than we imagine, but stranger than we can imagine. These puzzles are not failures of science. They are its lifeblood. They are the frontiers of our knowledge,